Welcome to this presentation on raw materials for e-textiles. In this presentation, we will analyze the materials and the components of the active smart textile systems and the definition of the intrinsically conductive polymeric yarns, and of the conducting, metal-coated and optical fibers. We will see, also, how various technologies like sensors, actuators, batteries, microcontrollers, antennas, Bluetooth can be applied in textiles and be wearable. Raw materials and components for e-textiles. The contents of this presentation are: summary of electrically conductive raw materials, sensors, actuators and energy supply, microcontrollers and wireless communication devices. Summary of electrically conductive raw materials. An e-textile is a textile with smart functions. In particular, conductive textile yarn or fibers interface with electronic devices and subsequently integrate into the textile materials. Many of the conductive yarns used are from metal yarns or fibers made from copper, stainless steel, silver, brass, nickel and their alloys. Other types of conductive materials are the conductive polymers, conductive coatings and inks. Metal coatings and conductive coatings are an area of intense study for applying non-conventional coating materials to textile substrates. Screen printing of conductive ink is one way to achieve it, but has its limitation. Several methods are being developed for conductive coating and other thin film coating applications. These include electro-less plating, where surface layers of metals are formed on the substrate via chemical reactions in a coating bath, sputter coating, where a thin layer of metal is formed by incident particles or ions accelerated by an applied electrical potential colliding with the surface, PVD, physical vapor deposition, where vaporized material is transferred to the substrate surface and deposits a thin film on it, and CVD, chemical vapor deposition, in which the surface is modified by depositing layers through chemical reactions in a gaseous medium. Conductive fibers and yarns can be divided into mono and multi-filament completely made of metal, alloys. The ability of intrinsically conducting polymers for electrical conduction originates from their electronic structure, as opposed to metal fiber or particle-filled conductive composites, which require significant concentrations of the filler to achieve a percolation threshold for conduction to happen. Conductivity is not an intrinsic property of the polymer structure but the property of the material as a whole. An optical fiber is a cylindrical light waveguide that exploits the property of light being refractive. It transmits light along its axis through total internal reflection. It is composed of a core surrounded with a cladding layer, both of which are made of a dielectric material, and possibly protected by a buffer coating. Optical fibers manufacturing consists of two major processes, by preform making influencing the attenuation and the dispersion characteristics of optical fibers and by drawing influencing glass geometry characteristics and strength. The materials used to produce an optical fiber can be glass, plastic and polymer-clad silica. In the area of smart textiles, optical fibers can be applied for data transmission, sensors, strain, compression, temperature and chemical substances, and for illumination. Sensors can be created by adding a periodic variation in the refractive index of the fiber core. Sensors, actuators and energy supply. Sensor is the device that has the function to receive a specific parameter from the environment, to create a signal, to transform that signal into another analog or digital signal and then to transmit it, with the purpose to be recognized, read and understood from another device or person. The classification of the sensors is basing on the parameters that they measure or on the characteristics that they have. Types of sensors. The ECG electrode or the electrocardiogram can conduct electric current. The EMG electrode or electromyogram can measure the electrical activity of skeletal muscles. The strain sensor is a device to measure the strain of an object. The temperature sensor is a sensor that measures the temperature of the environment and/or the body temperature. The pressure sensor is a device that senses pressure and converts it into an electric signal where the amount depends upon the pressure applied. The gas sensor measures the presence and/or the concentration of combustible or toxic gases in the atmosphere. The humidity sensor is the sensor that can measure the humidity, the moisture and the solvent based on the principles of the resistive resistance and the capacitance. The pH sensor is a sensor that uses halochromic materials, which are changing colors respect the varying pH environment. The optical textile sensors work with the variation of the light intensity or the amplitude that can be sensed by a fiber Bragg grating, FBG, sensor. Actuators. With the term actuator is defined the device that has the function to react under a specific parameter, which works like a trigger. This reaction can be an alarm, visual or audible, a vibration, or a temperature change, and the categories of the actuators are according by the type of the reaction, namely the outcome signal. On the other hand, the trigger who provokes the outcome signal can be chemical like a pH, oxidation, solvents, reduction or gaseous change, or physical as a light, deformation, temperature or electric change. Additionally, the way that works an actuator to have the reaction, determines the type of the actuator, who can be mechanical, chemical, thermal, optical or electrical. Types of actuators are mechanical actuator, thermal actuator, chemical actuator, optical or visual actuator, and electrical actuator. The sensors and the actuators, that do not use passive smart materials, need energy to work. This energy should be able at any moment that the user needs the properties of the garment, so storage systems are necessary in the development of an e-textile. The output devices, used in the textile sector, are light emission diode, LED, arrays, thermochromic ink, vibration, and shape memory alloys. The light emission diodes or LEDs are used on the electroluminescent-based displays. Conversely, the electrochromic displays or passive displays, in textile structure, are emitting multicolor lights, not by photons, but by using chromic or luminescent materials, as electroluminescent diodes, that reflect light in different ways. Nanoelectronics are electronic devices with extremely reduced size based to nanotechnology. They have the mechanical properties of the hybrid material, have semiconductors, single-dimensional nanotubes, nanowires, memory chips and displays, but the challenge is to have the same capabilities of the normal-size electronic devices, while their dimensions, weight and power consumption are extremely reduced. To create nanomaterials or existing materials should crumbled and modified to obtain required size and shape, or molecules of materials should be put in structural units to become nanomaterials. The nanomaterials, in turn, can be used for the creation of nano or microelectronics devices to be able their optimal integration into the fibers or the structure of the textiles. Microcontrollers. Microcontrollers is an embedded controller used in automatically controlled electronic devices. Any device that stores, measures, displays or calculates in electronic way, comprises a microcontroller. Practically, a microcontroller is a chip that works as a microcomputer and gives order to the other parts of the device controlling the functions of its system. The more requirements the device has, the more the microcontroller is potential. A microcontroller comprises components like memory, peripherals, and a processor. Microcontrollers are broadly classified into various categories based on bit configuration, memory, instruction set and architecture memory. The bit configuration is its potential of its accuracy and performance and is measured in 4-bit, 8-bit, 64-bit and 128-bit. The more bits, the more potential the microcontroller is. A further division is the two categories based on its memory configuration, the external memory and the embedded memory. Adafruit Industries designed two types of wearable microcontrollers, the Gemma and the Flora. Flora is more powerful than Adafruit's Gemma, but has 4,445 cm size, so is bigger, has a relatively small but efficient onboard reset button for rebooting the system, and the power supply is also designed to be considerably user-friendly. Flora also contains a built-in USB support, which means that the program shows up once plugged and it works perfectly fine with Mac, Windows, Linux, and any USB cable. Other wearable microcontrollers are, also, the LilyPad Arduino, Tiny Lily Mini and the Stitch Kit. Wireless communication devices. In general, everything that has to do with the communications centered on the human body is divided in off-body, on-body and in-body. The wireless communication in a smart textile could be by technologies that we already know as antennas, Bluetooth, Zigbee transmitters and receiver modules. Antennas are metallic structures that transmit or capture information and data by radio electromagnetic waves. To succeed the transition are able two antennas, so when the one transmit the other can receive the signal and opposite. In off-body communication, the antenna radiates away from the body. In in-body communication, the antenna is in the body, and in off-body communication, a system provides a communication link between a wearable system and an external base station. The conductive elements can be made out of electroconductive textiles or can be screen printed onto the substrate material. The frequency that is used for the data transmission determines the shape and dimensions of the antenna, so the smaller the operating frequency, the larger the antenna patch will be. Another way of wireless communication is the radio frequency identification tags, RFID. The integration of RFID tags into textiles gives interesting perspectives for the clothing industry. A garment could be traced from production stage to recycling, simplicity, the logistics and selection in transport and warehouses. The most commonly used technology in e-textile is Bluetooth. The last version of Bluetooth is 5.0, gives the max transmission speed at 48 megabits per second and a communication distance about 300 meters. Bluetooth can be considered as the PAN level of communication. The Bluetooth devices are divided into two categories: basic rate, enhanced data rate, and Bluetooth low energy, BLE. In e-textile applications can provide considerably reduced power consumption and cost while maintaining a similar communication range. Zigbee is another low power, low data rate and close proximity, wireless communication technology. In a Zigbee network, there are three kinds of Zigbee devices: Zigbee coordinator, Zigbee router and Zigbee end device. Zigbee end devices do not route traffic. They may also sleep, which makes end devices a suitable choice for battery-operated devices. Zigbee routers are responsible for routing traffic between different nodes. Routers are also responsible for receiving and storing messages. And at the end, a Zigbee coordinator is a special router. In addition to all of the router capabilities, the coordinator is responsible for forming the network.